All right, so let's get this thing started. Scott, Sui, I guess I have all of you here. So just a quick show of hand to kick it off. That how many of you are here because you wanted to learn about search infra? What about feed infra? What about like you're here because you know LinkedIn has a lot of good food? Okay, so now I know like what do I have to talk about. Just a quick rundown of what we want to do today. We're going to kick it off with Sui, who will tell you a little bit about what data infra actually does at LinkedIn. It will be followed by a presentation on feed infra, followed by search infra, and then we'll have a poster session. Before the poster session, Josh, who's the director of engineering here, he'll introduce you guys to the topics that we'll be discussing. So I hand it over to Sui. Let's go with that. Is this on?
Okay. Yes. Thank you for coming. I hope we will enjoy sharing what we do here with you, and hopefully by the end of the evening, you will enjoy as much what we have to share. Let me introduce myself. I'm Sui Lim. I run the LinkedIn data infrastructure team. This is the first meetup of the year for our team. In terms of data infrastructure, it encompasses all the back-end scalable systems we need to use to support our online serving systems as well as our nearline platforms. So it has three major components. It has the storage and media, which is all our distributed data stores that allow us to store and retrieve data very quickly from a source of truth perspective. It includes our streaming platform that allows us to build streaming applications. One of the major components there, which probably a lot of you are familiar with, would be Kafka. And then last but not least, which is relevance infrastructure, which supports our relevance activities in terms of indexing, retrieving large documents, and finding the most relevant information for our users. It also includes scoring ranking libraries, feature management that enables us to improve relevance agility. What you'll hear about today mostly will be components of our relevance infrastructure, about how we do feed, how we do search. If you are interested in our other pieces, our storage infrastructure, our streams infrastructure, I think there are some members of those teams here. I see our streams people here. Could you stand up, introduce, show your face? So if they are interested to learn more about our streaming infrastructure, they can reach out to you. Anyone from storage? No? Okay. So, yes, Sam. Sam's one of the managers on the streams team. Without further delay, let's move on to our first presentation. Hassan will introduce our feed infrastructure.
Thanks, Sui. I got the mic. I have a better mic than you. But okay. So just to kick it off with the feed infrastructure, there are three things that we'll be discussing about LinkedIn's feed. I'll give you guys like a quick overview of what our feed ecosystem is, followed by how do we ingest data into the feed, like how do people create content on feed, followed by how do we actually retrieve content from the feed. So basically you'll get a full picture of like how LinkedIn feed works at a very high level. And then all these poster sessions back there are going into a detailed depth of every system that we discuss here. So feel free to get your concepts from here and like feel free to ask any questions at the poster sessions or after my presentation. So to start off, like this is how LinkedIn's feed look like. Probably you guys are familiar with it. Like our mission here is to make sure that you guys are productive, the professionals are productive, and they're connected, and they're successful after seeing what we show on your link, on your feed. If you think about the feed, we broadly categorize it into two different sections or two different categories. So there are updates on the feed that you see. For example, Hassan shared a video or Hassan shared an image. And then you see updates like Hassan commented on something or liked something. And then there are some ads that you see over there as well as some job recommendations or news recommendations. So to classify these two types of things into different categories. There's organic updates, which you can see like comments, likes, and shares. And then there are recommendations like job recommendations and some ads. Feed basically is an ecosystem. So if you think about the feed, people are creating content. So they come there and like they create a comment, they create a share, they publish an article, they create a video, and so on and so forth. That creation of content needs to be explored by different people, which is discovery. So for discovery, we have feed as one of the avenues. People go and search for articles, people go and search for different people. So things that we are creating are getting discovered. And then while they're getting discovered, people engage with these things. So they like it, they comment on it, they interact with their network on that. So think of it, feed as an ecosystem where we create content, we discover content, and then we share content, engage with it, and we kind of like have this cohesive community around feed. Just to give you a very quick idea about like the scale that you are dealing with. We strive hard to give you guys a really good availability. We have tens and thousands of queries per second at any point in time in our systems. We have billions of organic updates per year, and we have tens of terabytes of data that gets produced. Millions of records per second are getting ranked within feed in order to actually present you with the best and the relevant content. So this will be your go-to diagram for today's presentation about feed. You don't need to absorb each and everything that is listed over here just yet. The way it would work is I'll walk you through different sections of this diagram, and as we talk through different sections, you will see how data or content gets generated in feed, indexed in feed, and then eventually retrieved in feed. I'll give you some time later on for question and answers. So let's talk about how content is getting created or ingested or indexed in feed. So this portion of your diagram will talk about it. The way it works is, let's say I come to LinkedIn and I create a share. I type in some comments, I type in some caption about that share. It can be an image, it can be a video, it can be an article that I'm sharing. So the content creation system, I'm just naming it as a black box over here, is something that is responsible for taking that content from you guys, run some pre-processing on it, do some checks around spam and whatnot in order to make sure that we have a good piece of content that gets created within LinkedIn systems. Once that content is created, the act of you guys creating that content is called an activity, which is basically the core of how feed gets generated. So if you think about activity, it is an active verb object triple where Hassan shared X. Umar commented on this, or Steve liked this. Everything is an activity, and we'll talk about it. So once the content gets created, the creation store calls into the activity store to create that act of doing this, of creating this content. That act gets stored into our Espresso DB, which is our key value store at LinkedIn, which I'm naming as Activity DB. So I created a content, the act corresponding to my content, which is an activity, gets stored into the activity store, and eventually the activity store stores that into a database. Now what happens after that? Before getting into that, let's talk about the stuff that I just touched upon, which is an activity, which is an AVO, which is actor verb object. So this is just an example. So Jeff shared a post. Jeff shared an article is an example of that activity. There are like a bunch of different things that we store with this activity, but like one of the important ones, just to give you an example, is visibility. That like while creating this activity, should this activity be just visible to your network or outside of your network or your first degree connections and so on and so forth. These are some common examples. So member connect member, member likes, member comments. We also have, like, when we talk about the A, which is the actor, doesn't necessarily have to be only a member. So there are companies who serve their content at LinkedIn. So a company shared an article, or a school shared an activity, or you would have seen these notifications. Sometimes actually people call them like very annoying. LinkedIn like congratulates someone on someone's anniversary at a company, right? So LinkedIn can be an actor, anniversary can be a verb, and company can be the object. The activity store, which is that part I just touched upon, is basically a wrapper around our key value store, which is called Espresso. And it does a few things. One, it creates that activity into the key value store, and then it has to transmit this activity across our system so that it gets available to other systems within LinkedIn. The way that does this is it just fires off of an event into a Kafka stream, which here I am terming as activity stream. Now that activity stream basically has all the activities that the user is doing, and what happens is that our activity index, which is a timeline index of different activities, I'll touch upon that. It actually picks up that activity from that stream and stores it into a store, which is a wrapper around RocksDB, in a way where you can easily retrieve timelines of different people. So we'll talk about what timelines is. This is exactly the slide that will show you how the activity index works. So this is our storage. Each one of these partitions stores a timeline. So M1, M2, M1 is member 1, M2 is member 2, C1 is company 1. Those circles that you see, think of those circles as activities. So let's say if I'm M1, I have done 2 activities. If I am M2, I've done 1 activity. And if you see that like each of this is a member partition index. So you can see that like all my activities are in partition 1. My friends' activities can be in a different partition, but all the activities for a certain member or a certain company are in the same partition. I'm just making things pretty simple over here for the sake of understanding. You remember that activities queue that we talked about? So the activities Kafka queue is where we will start ingesting the activities. So activities in the activity store basically created a Kafka event. Our partitioning cluster picks up, let's just focus on the last circle. So I picked it up, basically this one, I consumed it. Our partitioner just looked at the content of that activity and figured out that content is actually an activity for M3, the blue color you can see, right? So it put it at, it decided that I have to put it at M3. At that time, it picked up the first circle, which is the purple color, this one. It will pick it up. It figured out that it is for member M1, and it placed it there. So basically, an activity got created. The partitioning cluster made sure which member this activity was for, and it placed that into a member's timeline. Where timeline is simply a chronologically sorted list of your activities. So at this time, someone created an activity and it went all the way to the member 1's timeline. Does everyone follow that? Awesome, cool. So now when you're retrieving things for this index, what happens? So our querying cluster, basically, let's say it gets a request saying that get updates for viewer with network M1, C1, and M6. Let's say you are a viewer and I'm creating your feed and you have a network where you're following or are connected to member 1. You're connected to a company C1. You're connected to a company M6. To get their feed, we go to our query cluster. It checks out that okay, so M1, C1, and M6, they lie in these 2 different partitions. So we don't really go through all the partitions. We just go to that specific partition. We pull up the timeline, and then we pull up the timeline and eventually hand it over to the layers above us. So what is happening is, in order to generate my feed, what would happen is that for all my connections, I'm assuming all of you guys are my connections. So all my connections, we'll pull up your timelines and we'll eventually sort them together, merge them together, and hand it over to the layer above us. What happens after that, we'll talk about that. In doing so, I just missed one thing, which I purposely missed, that corresponding to every activity, there can be a lot of features that we need for relevance. So while we are consuming, we are retrieving all these timelines. For example, if I've been on LinkedIn for the last 7 years, I would have a really long timeline if I am an engaged user. So we have to bring the most relevant content back to you guys. And for doing that, we need a lot of features. So as part of the ingestion, it's not just the activities that we are consuming a lot of features about those activities. Features like that, like what is the global item popularity of this specific article? Is this article a spam or not? And like a ton of features, like we deal with hundreds and thousands of features in order to like come up with the most relevant content for you guys. Now, given the features, given the activities, I'm able to retrieve stuff. Now, I just touched upon something which is called spam. And there can be cases, let's say I share an article and someone comments on that and someone likes it. And later on, that article gets marked as spam. So in order for us to propagate the spam information or basically any feature information across all these objects, we need to have a graph of connections between activities. So here's an example of that graph. Let's say Jeff created a share, Joe created a comment on that share, and Jane created a like on that share, and that share itself contains an article. So activity graph is another pretty nifty piece of infrastructure that we own and we have created. By the way, there are blog posts about each one of these, so I can point you to those as well. So what happens is that like in order to propagate the features, we use the activity graph in order to propagate the features all across. So let's say that article gets marked as spam, we have the relationships between all the actors who have done activity around that activity, and then we mark those features across the board. So that takes care of like the generation of content within LinkedIn's feed at a very high level. So I published a share. The share got created into an activity. The activity got ingested into an index. The index is partitioned by members. When I have to generate someone's feed, I go to the relevant partitions. I extract the timelines for those members. I aggregated them together, and I just hand it over to the layer above me. Now, this is exactly what I just described, what is happening in the rest of this box. So the stuff that we talked about is the index stuff that we talked about is that black box, which is say that in-network activities follow feed. So there's a blog post on follow feed which you guys can actually check out for all the details. But now what happens? Think about the third box from the top, which is called feed federation. Actually, what is happening is that I just told you a very small piece of the picture where I only talked about activities that were getting sent back as the feed for a specific member. What actually happens is that the client calls a web tier, we call it Voyager within LinkedIn. You don't have to worry about the naming, but think about like a web tier which exposes a bunch of different APIs. And I call a specific API to get the feed for a certain member. Now, when I call that API calls another layer, which is the feed federation layer, which eventually calls a lot of different systems that hand over their recommendations for the feed. So follow feed is just one of those systems. Feed mixer, which is the federation layer, feed mixer is an internal name for that. What it does is that like when it gets the request to retrieve feed for different people, for a certain member, it will call follow feed, hey, follow feed, give me the timelines of all the connections for Hassan. I will give you like a really big list of all the connections, all the activities by my connections. Then it will call, let's say ads to ask that like, okay, any relevant ads that you want to show Hassan, any relevant JYMB, jobs you might be interested in, PYMK, people you might know, anything that you want to make part of the feed. So each one of these boxes, we call them as FPRs, which is the first pass rankers, submit their recommendations to feed federation layer that, hey, this is all the collection that you can use in order to curate the feed for someone. Now, feed federation layer runs a ton of different machine learning algorithms and makes sure that the second pass ranking, so just to be clear, there is a first pass ranking happening at each one of these FPRs, which is itself a machine learned algorithm, which hands over the best candidates to the second pass ranking, which takes care of like what should be the most relevant pieces that should be handed over to the user, and eventually it submits it back to the client. while doing that, it also observes what you guys are doing. Are you guys scrolling? Are you guys reading through it? Are you guys clicking? Are you guys commenting? Everything that you guys are doing is kind of used to make sure that we present you with the best content. Is kind of used to train the machine learning algorithms that we develop in order to present you with the best content. So while you are doing your stuff on the device, we capture some information that is captured in the stat server that helps us develop the best machine learning models, which we use with feed mixer, follow feed, and all the FPR layers in order to give you the best feed. So on the extraction side, basically a request came in, it gets panned out to all the FPRs. The FPRs joined the results together. Feed mixer, which is the federation layer, made sure to get the best content, and then it handed it over to the web client, and eventually you see the feed. So that's the retrieval picture that happens when a request to generate a feed occurs. So that completes a high-level overview of how content gets created, content gets retrieved from the feed. We still have 5 minutes, so do you guys have any questions? And then I'll hand it over to Scott. Questions? Yes, sure. If you want to ask a question, you can just completely come here. That's a mic right there. You guys can hear him? I can repeat the question, so you can go ahead. Yeah, so that's exactly the purpose of our activity graph, because if someone has reshared it, Hassan reshared that share is also an activity itself. So basically our activity graph has mappings from every activity and the doer or the actor of that activity. So let's say if an article gets marked as spam, we know that like which activities actually are the reshares of this article. We have that mapping. So we'll use the information that this article got marked as spam, we'll query through our activity graph and propagate that information across all the activities. Yeah. Oh, that's a great question. So how are features created dynamically? So the way it works is that like a lot of different teams are looking like the team where you're generating your content, teams are doing offline analysis of your content, teams are doing like, let's just take video as an example. We might just do like some transcript on the video to understand like what this video is about. And all that analysis happen offline. So once those features are created, we fire feature update, like basically feature creation events into this index. So that's actually a great point because this timeline index that I was talking about, it's not just an activity index, but we also have a local feature store in every partition. So let's say there is a spam feature store, which will store all the spam features for a certain activity. Similarly, there is, let's say, image feature store, which will contain the features for all the activities that have images. So long story short, we do a lot of offline analysis to generate these features, and then these features get indexed through that feature pipeline that I showed you. Yeah. And we can talk more about it. That's actually really good. Yeah. That's another great question. So yes, we have caching mechanisms up there, so we can take this offline in detail. Yep. But yeah, we do caching at that layer. Yes. Mm-hmm. Oh yeah, that's a great question. So the question is that like we have a lot of FPRs contributing to this federation layer, and then like it gets federated and delivered back to the client. So what is the latency of the response time, right? So at the federation layer, we have like a FPR-based timeout. So for every FPR, we have defined a timeout that follow feed should return within X milliseconds, and PYMK should return within Y milliseconds. And then at federation layer, we have an SLA for timeout, like that we need to federate the feed within these milliseconds. Otherwise, there's a concept around short circuiting where we short circuit that FPR and eventually curate the feed and hand it over. Now, the latency depends on the mobile versus web. And I don't know exact numbers, but like I can pull up exact numbers later on and discuss with you. Yep. Last question. Yep. That's a really good question. What's the experimentation story? So we do hundreds of experiments every day in order to make sure that we are doing the algorithms right. And experimentation is a core piece along every layer. So even let's say if we talk about follow feed, we do a lot of, we call them LIXs, but like think of it like as experiments. We do a lot of experiments to make sure that, okay, algorithm A versus algorithm B, which one of these is getting the best results back to the previous layer. And like the way we do that is like we have a certain group of people which are sharded by their IDs to a certain algorithm. Let's say I can ramp an algorithm to 5% and figure out like how we are doing. But that's a great question and we can totally talk about it offline after that. Cool. Thanks guys. So I would want to hand it over to Scott who can walk you through the search infra. Thanks.
Hello, can you hear me? Hi, I'm Scott Banikowski. Today I'm going to give you an overview of the search infrastructure here. And this is going to be a very high-level talk, kind of a mile-high view. I want to just give you an overall picture of what the major components are and also kind of highlight some of the open source technologies we leverage to build this. So my team is basically responsible for supporting all the search engines that run behind LinkedIn. And it's one of the main ways people interact with the website. This is, an example of one of our search pages. I wanted to call out a few things on here. First of all, you see this verticals across the top. That's, see, when I turn my head, I notice the sound goes down. So you can search for people, you can search for jobs, content, companies, et cetera, et cetera. Each of those is, we call it a vertical because it's a complete stack of our search engine. So they each have their independent search indices. And our team basically builds the reusable search infrastructure that can be used for all this different content. Other thing I want to call out is facets. When you do a search, you can find that you can drill in on certain parts of the search by specifying more concise constraints. These are called facets, and I'm not actually going to talk about it in this talk. I only highlighted it here because it was one of the things on the search page, and I wanted to mention that there's a really interesting blog post on how we do efficient faceting. If you look on our LinkedIn engineering blog site, it was posted there probably over a year ago, but a lot of our engineering effort goes into making facets really efficient because they can be expensive. In order to surface these facets, you have to look at almost the whole corpus of data. Lastly, there's the hits. This is what we're most focused on. These are the things that match your query. They need to be relevant to you. They need to be served fast enough to you. And so most of the work we do is in providing this speed and relevance. The two main components that we build are called Glean and Seize. Glean is a library that provides all the interface to the index, building the index, managing the index, and searching the index. Seize is the service layer that's built on top of it. It provides a REST interface so that it can be queried. It provides partitioning over multiple nodes. And it has all the plugins to the LinkedIn infrastructure, such as monitoring and all the goodness that goes into deployment. So these two things are what we maintain and build. If you're familiar with open source search, you may know about Lucene, Solr, Elasticsearch. If you think of it in those terms, Glean is our Lucene and Seize is our Solr. But Glean is built on top of Lucene. So we have Lucene as our low-level index, and we've added a bunch of things which are unique to our use cases to it. Some of you may not be too familiar with how search works. A lot of you might have some database experience or something, but may not have encountered search. So I just wanted to spend a couple minutes just describing at a very high level, how does a search engine work? Basically, it's building up a whole bunch of lists of terms to documents. So in this example, I have 3 simple documents, which represent like a small little profile of somebody that might be on the LinkedIn site. And when I build a search index, basically I want to be able to search all the terms that appear in people's profiles, such as their title or their name. So these terms are associated with the documents through what we call a posting list. For example, in company LinkedIn, all 3 of these profiles are in LinkedIn, so my posting list has all 3 documents in it. And you can see there's also 2 engineers, 2 named Jeff. There's 1 Juan and 1 CEO, which are also terms of this corpus, which I haven't displayed here, but they would also exist. So when you build your index, you basically want to take all the terms that are searchable and build these posting lists, and that's called the inverted index. And once you have that, then searching for terms really becomes just intersection of these lists. For example, if my query is, I'm looking for a guy named Jeff, and he's an engineer who works at LinkedIn, and when I put this query in out of my corpus here, I actually have 1 single match. If I intersect those 3 posting lists, I can see that document 3 appears in all 3 lists, and that's my hit. Now, usually things aren't that clean. Usually in a big corpus like LinkedIn has, you're going to get tons of hits. For example, if I was only going to search for LinkedIn engineer, then the posting list for Jeff no longer is relevant in my search. I only have to intersect these 2 lists, and now I've found 2 matches. At this point, I need to score and rank them and present them to you in the right order. One thing I want to call out here is that the ordering of these documents actually matters, because a lot of times for efficiency, we don't want to actually search the entire list. Some of these posting lists can be far too long, and it would take too much time to do all the scoring required to rank them. So often what we'll do is, well, we always put them in what we call static rank order, which means we look at the documents relevant to each other and try to put the ones that we think are most important up front. For LinkedIn and people search, those would be like the famous people and influencers are probably going to be in front of other people. For example, Jeff, the LinkedIn CEO, is probably going to have a much higher static rank than I have. But the static rank will come up later in this talk, so I wanted to bring it up now. So building an index is basically just taking the documents and creating an inverted index for them. We have to do this well, we have so much data here, we need a big data solution in order to do this, and Hadoop is the solution we use. So all of the data that we index gets ETL'd up into HDFS. And in fact, it lives there not just for search. There's a lot of products at LinkedIn which harness this data to do analytics, to do relevance training, to learn how people are interacting with the site and so forth. All this raw data is uploaded into HDFS, and then we can use Hadoop and Spark and other processes like that to analyze it and to work on it. So when we build a search index, we know all the raw data is there, but it's not all in one place. We first need to assemble it into documents. So the first step usually in building the index is to take all this disparate data, process it, sometimes massage it into the right format, and put it all into the documents. Once we have our entire documents, we can actually do a global ranking and determine the static rank for the documents and produce the inverted index for them. Since this isn't a single MapReduce job, it's actually a bunch of jobs, including Pig, which is another Hadoop solution that allows you to do some kind of SQL-like queries on data and data manipulation. We use that pretty heavily in pre-processing the data, and then we use MapReduce in building the index. So Azkaban is our solution for doing this. Azkaban is a workflow manager. You can think of your set of jobs that you need to accomplish something on Hadoop. If it's a DAG, some jobs can be run in parallel because they don't depend on each other. But in the end, these 2 jobs feed into another. Then you have this DAG of execution, and Azkaban can manage that for you. So we rely on Azkaban to run our Hadoop. And so the main steps are creating documents out of raw data and then indexing it. But that's just a simplified view. There's actually many steps involved. once we have our index, the next step is to get it to our clusters where we can serve it. Now, we have all of our data in Hadoop, a lot of sensitive company data there. So actually the Hadoop data center is isolated from the data center that actually receives customer traffic. So we can't just directly copy data from our Hadoop into our machines that serve them just because of these firewall restrictions and safety. So what we do is we have one tiny apple that we open up to copy the data over. So once we fetch the data into the indexers and searchers, and I haven't talked about what the indexers and searchers are, that'll be the next slide, but for now you just need to know that they both need copies of the index, and there's multiple replicas of them. So they don't just need one copy, we need one copy, and then we need to replicate it across many machines. To coordinate this copying and spreading of data, we use a product called Helios, which is, it's not an open source product, but it's built upon two open source projects. Those are Zookeeper and BitTorrent. So we use Zookeeper to manage the state of Helios, elect the leaders, for example, and notify other nodes in the cluster that the data is available for them to distribute. And then we use Torrent to actually distribute the data among them. And in addition to indices, we distribute snapshots. And snapshots are basically views of the data that have been updated since we built our base index. And this is part of the architecture, which we call our BML architecture for search. And I'm going to describe it here. This is probably the thing that when I joined about 15 months ago was the most surprising thing to me. That when we serve a query out of one search instance, we're not actually searching one of our indexes, we're searching 6 of them. And I'm going to explain why we have 6. So we have our base index. As I mentioned, it consumes a lot of data, and it's actually a pretty heavyweight process in terms of resources. It runs sometimes several hours, sometimes half a day, in order to build some of the indexes that we use. And so it's not practical for us to build it continuously to keep it up to date with the most recent updates. People are constantly updating data on LinkedIn, and we want to make it searchable immediately. We can't, if we were to wait for the base index to build, we would constantly be stale. So to keep this up to date, we accept live updates. And with that, we actually have real-time updates to all the data in search. In practice, it's a matter of minutes. So that means we can relax the schedule that we do this heavy process of building the base index. So our base indexes are actually built about once a week for most clusters. And in the meantime, we use the live index to serve all the updates. Now we have multiple live indexes that are in memory. As updates come in, we have 3 to choose from. The one on the left is called our BML segment. The one on the middle is called our ML segment, and the one on the right is called the live segment. So how do we decide where to put it? Well, it just depends on if we've seen the document before. So imagine I have a document that's already been seen in the base index. It already exists there. When I get an update for it, it's going to go into the BML segment on the left. When I get a document that I've never seen before, it's going to go to the one on the very right, the L segment. And what happens is occasionally this memory that we serve the index out of will fill up, and we need to process it into what we call a snapshot, which is our middle index. And so what we do is we take the updates that we've seen so far, we generate 2 snapshots, one for the ones that we've already seen in the base index, and one for all the others. The reason why these are separate has to do with static rank. When we built our base index, we know for every document there what its rank was globally. When we have a new index, when we have a new document that we haven't seen before, we don't know how to rank it in regards to the rest of the documents. So that's why it goes in its own segment, where it can be ranked mostly by time as the criteria. We can either serve the most fresh ones or the least fresh ones in that index. It's not until we build a new base index will they actually receive their global static rank. Another thing I wanted to mention was that the live update is different than the snapshot in the way it's represented. The live update is in memory, and The snapshot is actually a Lucene format. Now, Lucene format has been optimized for search. It's very efficient in terms of the space and in terms of the resources it requires to query it. But the one in memory is mostly just a set of Java structures. And it's not necessarily efficient to search, at least not nearly as much as the Lucene index is. And it is also causes memory pressure for us and garbage collection pressure for us because we keep these updates in memory. So the whole reason we build these snapshots is so that we can flush our live index out of memory and search more efficiently. So how do we get these snapshots? Well, and these live updates. Well, we have these updates coming in from all kinds of different sources. They could be, in this example, I have profile updates, like you've changed your title, so that would be an update that would go to our index. Or you have a new connection, that connection can go to your index. Now, unlike some other search engines, like including Lucene, usually when you update a document, you have to rewrite the entire document to re-index it. One of the innovations of the LinkedIn search is that we can actually do a partial update. We don't need to update the entire document in order to build an update for it. So what we do is we take all these partial updates and they go through a process called our live updater. The whole job of the live updater is basically to convert that into a document or into a partial document, which then gets fed to the searchers and the indexers. Now the searchers are what serves the queries. Those are taking the live traffic and giving you the responses. The indexers are almost like searchers in that they do the same thing with building the index, but rather than taking live queries, instead their whole job is to generate snapshots. Generating a snapshot is not, it wouldn't be able to do it on a searcher just because the process of generating the snapshot would be too intensive to also serve query traffic at the same time. That's why these roles are divided. So they both have the same kind of in-memory handling of all the updates. The difference is searcher runs queries and indexer just continuously builds snapshots. And usually the time of a snapshot is about roughly 1 hour, maybe every hour, but it depends on how many live updates are coming in. Basically we flush it if enough time has gone by and we haven't created a new one, or if we see that the memory pressure is getting too high. What happens after we get a live update is the indexer will publish that it has a live update to Helios, which is writing into Zookeeper and then spreading it around through Torrent. So all the searchers of that same partition can now pick up this new snapshot. And what happens is that when they see the snapshot has been downloaded to their Torrent client, it's time for them to pick up the snapshot. So what they do is they de-announce saying that they're no longer accepting traffic. They drain their traffic. They go down, they reload the snapshot, and they come back up. When they come back up, they can dump their live updates because now they have a snapshot that's almost up to date. However, there probably are some updates that have come in the time that they went down and picked it up. But what we have is this Kafka queue, which feeds these updates to the indexers. And with Kafka, you can actually go back in time. So in the snapshot, we have a timestamp of when the snapshot was created, and we know exactly where we need to go back in the Kafka feed to resume and pick up all the snapshots so that we're always up to date. And then we can announce again. And we use Zookeeper to coordinate our nodes going up and down so that not too many nodes go down at the same time. That way we always have enough replicas around to handle the traffic load. In addition to searchers, we have brokers. So the whole role of a broker is to talk to multiple partitions. Most of our indices are far too large to sit on a single partition of a search engine. So like our largest clusters, we have 64 partitions. Each of those have a slice of the index. So if you imagine we have all the member profile and you hash on member ID 64 ways, then you'll see the members are distributed over these 64 partitions. So the job of the broker is to take in a query, fan it out to all the searchers, and have once all the searchers respond, then they can merge the results and return it. Now, I'm going to go back to a previous slide here. One thing I didn't mention when I talked about this was that we actually divide this data. It was structured. These documents had fields like name, title, company. When you run a query, you can see the query was like company LinkedIn, title engineer, name Jeff. But if you've ever used LinkedIn search, you probably didn't type in the structure that you wanted to find the data in. That job is partly done by the rewriter. So when you write in a raw query, the job of the rewriter is also to rewrite that query into something that is specific to the search index and more likely to retrieve data. And I think I've covered all the components. And if you had a chance already to check out the slides, you may have already seen this poster in the back. This poster basically highlights all the components and shows you some of the open source things that we leverage here. And I have a lot of time left, so if there's questions, I can take them. Yes? Pardon? Okay, the question is, why do we need to generate a base index every week rather than just perpetually taking live updates? Mostly for the global ranking. When we build a base index, we have a view of all the documents, and you can do that global ranking. Maybe it's possible without it, but you probably need to come up with a really good heuristic for doing ranking against each other documents without seeing the whole corpus at one time. Yeah, in the back. Okay, so the question is, what does global ranking or static ranking mean in absence of a query? It mostly has an optimization for early termination. And so you want to have the most important, what you perceive to be the most likely relevant documents to have a higher rank, because if you need to terminate your query before you can examine the full posting list, then you would know you have at least hit the high quality documents. But there is re-ranking which happens, and a lot of the expense spent in executing a search is actually in scoring the document, and in that case it's definitely using the query as input to test scoring, and it's trying to match based on the query. Well, it's a representation of yeah, goodness. If you're familiar with Google, like LinkFlux is a static rank, and it's not the only thing they use, but it goes into the algorithm. You can think of at LinkedIn, if it's a profile, then their connections might be this equivalent to LinkFlux, and so somebody with a lot of connections will probably search for more, and therefore they're probably a higher ranked. The question was what do we search for? Does it include the feed, et cetera? So yeah, I think we do have a vertical that searches articles that comes in from the feed. We actually built a whole bunch of things for search that aren't even customer facing. For example, for the engineers here, we have a code search, and all the data, all of LinkedIn's code is made searchable using our own search engine. So that's one example of like dog fooding our own code. Yeah. So the question is when a new, well, you use an example of company, but it could be anything, gets created, what is the SLA? So, I mean, we strive to be real time. I think in practice, it's about minutes. Usually it's about how quickly we can process those Kafka queues. So the question is, I think basically you're wondering why we used BitTorrent. Oh, okay. So you think like spreading around using a tree communication network to spread the index, and yeah, that would work too. Yeah, in the back. So the base index, it depends a lot on which index it is. I think the longer ones take up to 8 hours for the largest of our indices, which are quite large though. We could start the next build immediately, but it wouldn't really solve our freshness problem because it would still be 8 hours stale. And also, you know, that it's pretty heavyweight to build, and we need to share the Hadoop cluster with other customers as well, other customers within LinkedIn. If we were hogging the Hadoop clusters to continuously build indices, then I think everyone else would be mad at us. So the question is, why do we need to keep building snapshots as opposed to just keeping them in memory as an in-memory structure? Okay, yeah, so his follow-up question was, if we lose a node, do we lose the data that's in the live update? For that instance, yes, we lose it, but it's also in the Kafka queue. And when the node comes back up, it also looks at the latest snapshot it has, and then it re-ingests from the Kafka queue all the live updates. So it does the data. It's persisting, but it's making it much more efficient. Remember, the snapshot format is in Lucene index, which is optimized for search. The in-memory ones are not, it's not easy to build a Lucene index on the fly. It actually takes some batch process to do it. And so that's why we have the indexer node, which is building the snapshots, because it can do that batch process, where the searcher nodes can't be doing the batch process at the same time they're serving query. It would just be too much memory pressure. Yes. Yeah, his question was just clarifying that middle index is, live updates are just to make the data available right away. Yes. Yes. So his question was, are the indexers and searchers duplicating data? And they actually do duplicate the same data in memory while they're building the live index and while they're building Snapchat. Right. So once an indexer builds a snapshot, then it just starts pulling in new updates and starts to wait to build this next snapshot. And then the searcher doesn't need to build the snapshot, it just picks it up. Yes. So the question is, how do you manage schemas? Are you talking about the index schema? So the index schemas are checked in. Like, basically, we have a schema format, which is an XML file. And those get checked into our code. Yeah, so to add a new, like if you want to change the index, basically you have to wait until the new base index gets built into the until it becomes active. Okay, so I think I'm going to cut it off now and introduce Josh, who's going to say some closing remarks.
On now? Yes? All right. So I'm Josh Walker. I've got the privilege of leading Relevance Infrastructure. As we described, Relevance Infrastructure is part of our data infra family. Relevance Infra includes the feed stack, which you guys heard some about today, the search stack, as well as recommendation systems and data production pipelines. So all of the systems where we kind of thread through relevance and ML modeling to serve the best results. I think we've got a slide on the poster sessions. So we're not done yet. Show of hands, who learned something tonight? Hoping all the hands would go up. LinkedIn people, you didn't learn anything? All right, so that's your job now. We'd love to keep talking to you. We've got 6 great poster sessions. I'll describe them in a second, but we want this to be interactive and we want to learn from you. Hopefully you can teach the LinkedIn team some things about what you work on, or at least give them some hard questions to try to answer. So the poster sessions, we've got one on follow feed. As a reminder, that's the guts of the feed stack, the timeline index. For the search folks in the room, it's a term charted system, so you might ask the team why they decided to do that. Feed Mixer is kind of the top of the feed stack where all the different content gets blended together. It's where we do a lot of the heavy lifting for relevance. So great topic for those of you that are more focused on the ML side. And the activity graph, we had a good question earlier about how we propagate spam through the denormalized data structures. Activity graph is how we do that. Moving on to search, so Glean, the core Lucene wrapper, if you will. If you're into algorithms, data structures, the bit twiddly stuff, that might be the poster session for you. Distributed systems, Cs, if you wondered why we use BitTorrent, how we use Zookeeper to do leader election, that's the poster session for you. And then if you're a big picture system architect, the search distributed data flow, I think I flipped 2 of them around, but you'll find the right poster based on the pictures. We've got a big picture search system there as well. So as I said, thank you very much for coming. We had great questions. I hope we'll get more in the poster sessions. If you're just curious about the food, we'll have engineers that can tell you about that. And I should plug Sam and the Streams team. You guys are still around somewhere? Sam? Yeah? Okay, well, we've at least got Greg and some other folks. So if you're interested in other parts of LinkedIn's data infrastructure, I'm happy to talk about that. Greg can talk about it. We'd love to talk and exchange ideas. Before we do that, Hassan's going to help me with our last thing, which is the drawing for the Google Home. I think you all have a ticket probably that we're going to need to match a number on.
I guess what should be the best way of doing it? Maybe we can have one volunteer from you guys who can come and pick up. It's still working, right?
Would you mind drawing?
Sure.
So just don't draw your own ticket. That'll look bad. Okay. So the number here is 884054. 884054. Do we have a match somewhere?
Okay, we have a match here.
All
Cool.
right.
Thank you.
Let's check. We're all into data integrity here. Yeah.
Congratulations.
Thank you. Congrats.
Thanks, guys.
Thanks, everyone. Enjoy the beer, the food, and the poster sessions.